Hello everyone, I'm Yifan Dai. Today, I'll present Symbiosis, a framework for application and kernel cache coordination. This is a joint work with my colleague Jing and my advisors Andrea and Remzi. Today, large-scale database systems like RocksDB, MongoDB, and MySQL are widely used. They are embedded with storage engines like RocksDB and WiredTiger to interact with the underlying file systems. For performance purposes, storage engine applications use data caching. Implicitly, there is another layer of kernel caching, that is the page cache. Many storage engines utilize data compression to save device I/O, so that the kernel caches compressed data from the device and the application caches uncompressed data. This forms a unique application kernel two-layer cache structure. The two cache layers share the same memory quota. Here, we highlight the memory partitioning problem between the two caches. It can yield great benefit if we do it right, but doing it right is not trivial because it depends on various factors such as working set size and access pattern. For example, let's consider one varying factor, the working set size, and two simple cache size configurations. One is giving all the memory to the application cache, and the other is giving all the memory to the kernel cache. Accessing the application cache is faster than accessing the kernel cache, but the kernel cache essentially stores more data in memory because of compression. When the working set is small, giving all the memory to the application cache could be 2x faster than giving all the memory to the kernel cache, because the application cache holds all the data. But with a larger working set, giving all the memory to the kernel cache could be 5x faster instead, because the kernel cache still holds all the data in the compressed form. Therefore, it incurs far less device access than the other configuration. According to our study, the best cache partition could vary a lot depending on workloads and environments. In this work, we built Symbiosis to solve the cache partitioning problem. Symbiosis is a framework for key-value storage systems that configures cache sizes to improve performance. It embeds a module in the application that automatically optimizes cache sizing by online simulation. Further, to do with dynamic workloads, Symbiosis detects workload change and adapts cache sizes accordingly. Symbiosis is integrated into 3 production systems, each within 1,000 lines of code change. It improves performance by 1.5x on average for read-heavy workloads. Symbiosis applies several optimization techniques to achieve high accuracy in online cache simulation while incurring negligible space and time overhead. In this talk, I will first give an overview of Symbiosis, then talk about the key challenge, that is how to simulate accurately with low overhead. Then, we will dive into several optimization techniques to solve the problem. Finally, I will show the evaluation on various static and dynamic workloads. Symbiosis works in the following steps. First, it detects workload change by monitoring cache performance. Upon workload change, Symbiosis starts to simulate a set of candidate cache size configurations. Then, the expected performance of each candidate is predicted and the best configuration is selected. Finally, the best configuration is applied if it yields enough benefit. To get robust performance improvements, we must accurately predict the performance of the candidates. On the other hand, we want to incur negligible overhead during simulation. There is a tension between the two objectives. A naive full simulation with the highest accuracy would incur unacceptable overhead. Therefore, we propose several optimization techniques to achieve both high accuracy and low overhead. A classical solution for cache simulation is to use ghost cache. Unlike a real cache, ghost cache leaves out data and stores only cache access metadata, such as the keys. It is useful for cache stats analysis when only hit-miss results matter. We want to use a single ghost cache instance to simulate all candidate configurations to reduce memory consumption. In the case of a single-layer cache, when the eviction policy has stack property, such as LRU, this is easy. One can simulate caches of different sizes simultaneously by recording the positions of hits. In this example, we have one ghost cache instance and two caches with size 2 and 4. An access to cache entry 1 is counted as a hit for both caches. An access to cache entry 4 is counted as a hit for the larger cache and a miss for the smaller cache because the hit position is beyond the ladder size. But in the case of a two-layer cache structure, the previous technique no longer works. The reason is that the second layer sees different access patterns if the first layer is sized differently. Let's look at an example. We have a trace with skewed access to entries 1 through 3 and occasional access to entry 4. Accesses that are missed in the first layer go to the second layer. If the first layer size is only 1, it misses all the accesses, and the second layer sees the same skewed access pattern to entries 1 through 3. With the same trace, if the first layer's size is 3, most of the accesses to entries 1 through 3 hit in the first layer, but all accesses to entry 4 miss and go to the second layer. Then, the second layer sees a different access pattern that is skewed to entry 4. Thus, it is not possible to simulate these two configurations simultaneously. In Symbiosis, we achieve the goal of using only one ghost cache instance by incremental reuse of that instance. With only one instance, we need to simulate multiple candidate configurations one by one. We can always reuse the contents of the first layer application cache because of the stack property. The question is how to deal with the second layer kernel cache. Before each simulation, we insert a short warm-up period to let the contents of the ghost cache approach the next configuration. We then design a simulation order of increasing application cache size so that we minimize the difference between neighboring configurations to minimize the warm-up period. Even with one ghost cache instance, its memory consumption is still too large. Thus, we incorporate key space sampling to further reduce the overhead. Key space sampling is widely used in cache analysis, which uniformly samples targets in the key space and all accesses to the sampled targets. In this example, 3 targets marked in gray are sampled. Then only the accesses to the sampled targets are kept. This sampling method also works in normal multi-layer caching. But there is another property in our application kernel cache structure that is misalignment. The original sampling method doesn't work well with misalignment. So, what is misalignment? The application caches in the unit of blocks of uncompressed data, while the kernel caches in fixed-size pages of compressed data. They may be in different sizes and misalign with each other. In this example, the gray block in the application cache key space corresponds to two gray pages in the kernel cache key space. To understand why the original key space sampling doesn't work with misalignment, consider this more complicated example. The 2 gray blocks in the first layer have been accessed, and it corresponds to 4 gray pages in the second layer. Now we access the blue block. Note that the corresponding pages in the second layer have already been touched by previous accesses to the neighboring blocks. Thus, this would be a hit in the kernel cache. But since key space sampling uniformly samples the key space, it is unlikely to sample contiguous targets. So the blue block is not sampled, and the additional hit in the kernel cache is not counted. Essentially, misalignment affects accesses to contiguous pages more, but key space sampling loses such effects. Thus, it could result in a very inaccurate simulation. The graph shows the hit rate of the kernel cache of different sizes with and without sampling. The y-axis is the hit rate, and the x-axis is the cache size. The gray line does not use sampling, and the orange line uses the original key space sampling. We can see that their hit rates differ a lot. Since the effects of misalignment are significant when contiguous targets are accessed, we propose misalignment-aware sampling that always samples contiguous targets together. In this example, we sample 3 contiguous blocks in the first layer as a group. Misalignment-aware sampling gives us a much more accurate result. In this graph, it is the blue line, and it approaches the hit rate curve of no sampling much better. Besides misalignment, there are many other properties and optimizations in the kernel that may also influence the kernel cache hit rate. For example, read ahead. To reduce overhead, we choose not to precisely model all these features. Then, there would be a few corner case workloads where our simulation is not accurate. The graph shows an example in the normal case where simulation is accurate. The y-axis is the performance where higher is better, and the x-axis is the application cache size of different configurations. The dashed line is the current performance, and the solid curve is the simulated performance of different configurations. Each point represents a configuration. The best performance takes place at the rightmost point and is better than the current performance, so we adapt to that configuration. Now, what happens if the simulation is not accurate? We have an observation that omitting kernel features in simulation tends to make the simulated performance worse. As shown in the graph, all the simulated performance are worse than the current performance. Thus, we have a policy that only adapts to a new configuration if the simulated performance is better than the current performance by a threshold amount. This way, we not only rule out inaccurate simulations in unmodeled cases, but also generally avoid adapting to a worse configuration. In this example, we simply reject all the simulated configurations and keep the cache size as is. We evaluate Symbiosis with various static and dynamic workloads. With static workloads, we evaluate Symbiosis' ability to find a better cache size in various workloads and environments, and its generalizability to different storage engines. We integrate Symbiosis in 3 production systems and run over 190 workloads with different dataset sizes, access patterns, compression algorithms, and hardware. Symbiosis performs better or equal to the best static configuration in 98% of the workloads, with an average gain of 1.5x over each static configuration. In dynamic workloads, we evaluate Symbiosis' ability to detect and adapt to workload changes and analyze its overhead and tail latency. Symbiosis properly reacts to workload changes in all of the 38 dynamic workloads. Its online simulation incurs only about 0.1% space overhead and 1% time overhead. I'll show how Symbiosis works with an example dynamic workload. The example contains two static workloads, and the workload change takes place in the middle. The first workload is very skewed, while workload 2 is not. Both datasets fit in memory when compressed, but not when uncompressed. In the graph below, the x-axis is the progress of the workload, and the y-axis is the latency per operation, where lower is better. During workload 1, if we give all the memory to the kernel cache, it has a steady performance of around 6 microseconds per operation, as shown in the blue line. If we give all the memory to the application cache, it performs better because the workload is very skewed and the application cache holds the entire hotspot. This is shown in the orange line. Symbiosis is the black line. It performs a round of simulation at the start of the workload, then adapts to a better cache size with lower latency than both static configurations. During simulation, Symbiosis has the same cache size configuration as the blue line. Its latency is also the same as the blue line during simulation, showing that Symbiosis incurs negligible overhead. The line plot shows how Symbiosis works. The line plot shows how Symbiosis simulation works. The y-axis is the performance where higher is better, and the x-axis is the application cache sizes. The dashed line is the current performance. Each configuration is simulated one by one in the order of increasing application cache size. The solid curve is the simulated performance. Symbiosis finds that giving about 40% of the memory to the application cache performs the best. The expected performance is better than the current performance, so we adapt to that configuration. Now let's proceed to workload 2. The blue line, giving all the memory to the kernel cache, performs similarly because the kernel cache still holds all the compressed data. The orange line, giving all the memory to the application cache, performs worse because the workload is less skewed and the application cache no longer holds the entire hotspot. The black line, Symbiosis, detects the workload change, starts another round of simulation, adapts to a new configuration, and performs better. The line plot shows the simulation result. Again, the best performance takes place when we give about 40% of the memory to the application cache. In general, Symbiosis takes some time for simulation and find a better configuration. Then, it changes the cache sizes, which may incur a small latency peak, and achieves performance gain after that. In conclusion, Symbiosis is a framework that adjusts cache sizes dynamically by online simulation. It is integrated into 3 production systems, each within 1,000 lines of code change. It adapts to various workloads and environments and properly reacts to workload changes. It delivers an average gain of 1.5x for read-heavy workloads, with only about 0.1% space overhead and 1% time overhead by carefully designed optimizations to online cache simulation. From a broader view, we advocate the approach of simulation-based online performance tuning, especially when dealing with the dynamic nature of modern workloads. Unlike machine learning-based tuning, where high-quality dataset is important, simulation-based approach is generic and relies on deep understanding of the underlying system and the performance space. For example, as shown in our work, system behaviors such as misalignment are important to cache simulation. By making proper trade-offs and optimizations, there is a high potential of simulation-based parameter tuning of other knobs beyond cache sizes. Please refer to our paper for offline simulation study and detailed implementation and evaluation. We have open sourced our framework and workload traces to help with further investigation. Thank you for listening.